Let us now see the decimal expansion of real numbers. You know that real number is a collection of rational numbers and irrational numbers. You have a good friendship with rational numbers. So let us first take up the decimal expansion of rational numbers, and then later on we will take up the decimal expansion of irrational numbers. To understand the decimal expansion of rational numbers, I have taken three rational numbers. Those are 10 by 3, 7 by 8 and 1 by 7. For all these three rational numbers, I have already done the division here. You need to observe these divisions carefully and tell me what do you notice. I am sure you all must have noticed that here the remainder is 0 and in these two cases the remainder is not 0. So what happens here? After a certain stage the remainder becomes 0, and here after a certain stage the remainder starts repeating. You can see the remainders are repeating. So that is our first point. What is our first point? That after a certain stage, either the remainder becomes 0 or the remainder starts repeating. What else do you observe? See here, the remainders are all 1 and the divisor is 3. Here the remainders are 6, 4 and 0 and the divisor is 8. Here the remainders are 1, 2, 3, 4, 5 and 6 and the divisor is 7. So what do you notice? I am sure you must have noticed that the divisor is always greater than the remainder, or we can say that remainder is always less than the divisor. So this is our second point, that the remainder is always less than the divisor. Here you can see all the numbers which are lesser than 7 are there in the remainder. 1, 2, 3, 4, 5, 6. All these numbers are lesser than 7. So you can have maximum how many remainders when the divisor is 7? 6. Now let us take up the third point. What else do you observe? So when the remainder is not 0, you can see here the remainders are repeating, the quotient is also repeating. Similarly here, when the remainder is repeating, the set of blocks of numbers is going to repeat. You can see here, the quotient is repeating. You can see I have made a horizontal line here and I have made a horizontal line here. This is called bar. All the digits which are written under the bar, those set of digits, they will be repeating. Here all these numbers will be repeating because they are under the bar. Similarly here 3 will repeat because that is under the bar. Let us now conclude the decimal expansion of rational numbers. So you have two cases in the case of decimal expansion of rational number. The first case is when the remainder is 0. When the remainder becomes 0, the decimal expansion of the rational number terminates. So here in this case, the decimal expansion of 7 by 8 is 0.875, that is terminating. In the second case, when the remainder is not 0, you can see that the decimal expansion of the rational number is non-terminating, repeating. Here these set of numbers, they are not going to terminate, they will keep on repeating. Here also you can see this 3 is going to repeat. So in the second case, the decimal expansion of rational number is non-terminating, repeating, or you can use the word recurring. And you know that numbers which are not rational numbers are called irrational numbers. So what else do you think is left out in the decimal expansion? Only one case, where it is non-terminating and non-repeating. Moreover, if a number has a decimal expansion which is non-terminating, non-repeating, we can say that it is an irrational number. Similarly, we can say it for rational numbers as well. The numbers which have the decimal expansion as terminating or non-terminating, repeating, those numbers are called rational numbers. Let us understand with the help of few examples. Show that 3.142678 is a rational number. In other words, express 3.142678 in the form P by Q, where P and Q are integers and Q is not equal to 0. So you can clearly see this is a terminating decimal number. That means it is a rational number. So rational numbers, they are always expressed as P by Q form, where P and Q are integers and Q is not equal to 0. To do that, it is very simple. Let us do it. So it is 3.142678. We can rewrite this as 3142678. You can clearly see here the decimal point is after how many digits? 1, 2, 3, 4, 5, 6. So we will divide this number by 10 lakhs. That means it has got 6 zeros. So when you divide this number by 10 lakhs, you will get this number again. So you have already written now in P by Q form. Here this is integer, this is also an integer, and denominator is not equal to 0. So you have expressed this terminating decimal number as a rational number. Now let us take the next question. Show that 0.2353535 and so on is equal to 0.235 is under the bar. Can be expressed in the form P by Q, where P and Q are integers and Q is not equal to 0. So you can clearly see that this decimal expansion is non-terminating, repeating or recurring. So this is a decimal expansion of a rational number. So that is what they are asking here, to write down this in the P by Q form. Let us see how to do it. So what we are going to do here, we are going to assume this rational number to be x. So let x be equal to 0.235 bar. So here you can see 2 digits are under the bar. So we are going to multiply both the sides by 100 because here 2 digits are under the bar. If there is 1 digit, then you will multiply both the side by 10 if 1 digit is under the bar. So let us now multiply both the sides by 100 because there are 2 digits under the bar. So when you multiply both the sides by 100, you get here 100x. And when you multiply this by 100, the decimal point will shift here. So it is here as of now, so it will come here. So let us write it down. This is 23.535 bar. So when you multiply by 100, you will get this number. Now what we are going to do, we are going to subtract 1 from 2. We will subtract 1 from 2. So we will subtract the left hand side with left hand side and right hand side with right hand side. So 100x minus x, what will you get? 99x. So here when you subtract x from 100x, you get 99x. Now let us subtract this side. So I'll show you how to subtract. So from 23.535 bar, you have to subtract 0.235 under the bar. 0.235, this is under the bar. So when you subtract it, this will be cancelled. So you will get 0 here. 5 minus 2 is 3. And here you will get 3 and here you will get 2. So what will you get? 23.3. So here you will get 23.3. Now we will bring 99 to the other side. So here you will get 23.3 upon 99. So this has to be integers. This is a decimal number. To convert into integer, I will multiply both numerator and denominator by 10. So when you multiply both numerator and denominator by 10, here you will get 233 and in denominator you will get 990. So the rational number is 233 upon 990. So if you divide this, you will get the same decimal expansion. Now let us discuss two famous irrational numbers, root 2 and pi. This is a decimal expansion of root 2. You can clearly see here, this is non-terminating, non-recurring. To find out the decimal expansion of root 2, you can use long division method. This is the decimal expansion of pi. This is also non-terminating, non-recurring. Now let us take this question. Find an irrational number between 1 by 7 and 2 by 7. So you have to find one irrational number between 1 by 7 and 2 by 7. There are infinite irrational numbers between two given numbers. Here you have to just write down 1. To do that, first write down this rational number in decimal form. Similarly, write down this number in decimal form. How will you do it? Just divide 1 by 7 here and divide 2 by 7 here, and you can get the decimal form. So you have to write down an irrational number between these two rational numbers. That means it should be greater than this and it should be smaller than this. So 0.2. You can clearly see that this is greater than this, but this looks like equal. But if I put here 6, then this is smaller than this. So you need an irrational number. That means it has to be non-terminating, non-repeating. So what I'll do is I'll write down 1, 0, 2, 6, 1, 0, 0, 2, 6, 1, 0, 0, 0. So, and so on. So you can clearly see that this is non-terminating, non-repeating. Like this, you can write down as many irrational numbers you want.